Thank you for coming today. My name is Tsai, and my coworker Hua. We are working at Netflix, and I'm Spark committer, and he is the lead developer on this work. So I'm just going to give an intro, and I'm going to give him talk about the detail. So as you can see, Netflix is the house of data, the house of data as well. So we have so many data, and just give you some idea about how big the traffic we have and how much data we are processing. Here is the picture of the how scalability is our infra. So right now we have more than 100 million of the members right now, and we are global, which is the biggest news last year. And we support many different devices, and a third of the US internet traffic is from our service. So as you can imagine, for so many different device and country, we want to build a customized experience for our users. So we need to process those data and see the common behavior between different people and build a recommendation system for them. So recommendation, what we want to achieve at Netflix. So what we want to do is that whenever a member signs into Netflix, when they turn on the Netflix, we can press something they want to watch at that moment automatically for them. So this is the goal we want to achieve. Although it's pretty hard and it's really ambitious, but that's the goal we are trying to achieve by doing machine learning in a data-driven way. So everything at Netflix is recommendation, from how we rank the title in a row, or how do we rank different row in the whole page. And in fact, majority of the traffic, actually more than 80% of the traffic, is from our recommendation systems. So I'm going to give you a little bit background about how we run experiment, and talk about why Spark is really important for us, and how Spark helps us in terms of scalability. So for experiment, we try different idea, using historical data based on the past behavior, and see whether we can get better result for user. And we have a metrics to evaluate what's better. Can be the ranking metrics, or when the model is bringing it into the A/B test or production environment, we can test it based on all the user engagement, or how they like Netflix, how long is the streaming hour, this type of the real metrics to benchmark the model. And the reason why bringing the model from offline to online to test it is important, because as you guys know, recommendation system is basically a feedback system. So majority of people see what they want to watch, and we give a model, and they can bias users' behavior. So the training data can be changed based on the model. So it's a feedback loop. So we need to have a A/B test environment to test out how the model actually look like, instead of just working on the offline metrics. So here is the typical pipeline, how we set it up, an experiment at Netflix. So we design experiment first. We collect the historical label data, and we do feature generation offline. And then we train the model on top of the offline feature generations. And today we're going to focus on offline feature generation, because this step requires processing a lot of data from different tables, join them together to create the data in order to do model training. So we're going to focus on this step today. And then after train the model, we compute a validation metrics, can be any ranking metrics. And then we test the model. And if it doesn't work well, we go back and design a new experiment. And if the offline metrics go well, then we deploy it online to do online A/B test. So we create a framework called DeLorean for feature generations. And then the first step is we define the model, which is the experiment, what kind of feature you want to have. Can be like a user label features, or can be video metadata, or can be some feature joined together by video and memo data. So we design the experiment, and we collect the labels from the historical data. And then we get the required data from S3, which we store as Parquet file for the historical data. And we fetch the data from the snapshot to the DeLorean. And then we have feature encoder defined, how we productionize the feature, the business logic, and those code will be reused in the production environment. So feature encoder is shared between offline and online systems. And then we create a feature for model training. So as you can see, there are many join happening in the whole framework, including the label, how you join with snapshot, and also how you join with the feature encoders. So the idea here is that for those join, we want to utilize Spark to optimize the performance as much as we can, such as predicate, pushdown, this type of stuff. And we want to avoid converting those data into RDD. We want them stay in data frame as much as possible. However, many of the operation is not implemented in data framework. So sometimes we need to customize it to achieve our goal. And previously, we sometimes do some kind of RDD conversion and apply some logic, and then convert it back to data frame that requires some serialization and deserialization. So who are going to talk about how we address those problems by implementing the customized catalyst expression that is natively in Spark, so Spark can use it and in an optimized way to achieve the best performance. So let's hand over to Hua today.
Thanks, DB. So I'm going to talk about implementation details of our offline feature generation engine. So as DB said, we store historical data, and we run our training pipeline offline to get features and get predictions for that. So I'm going to talk about the details of the implementation. Over the years, we have multiple implementations of the same thing, this offline feature generator. The very first version is based on RDD operations. So at that time, when we first wrote our offline feature generator, there were only RDD APIs available, so we used that. So there are several aspects of opacity about RDD operations. The first aspect is that data are opaque. By opaque, I mean Spark has no information about what's inside of that. It's just a distributed collection of Java objects. So Spark doesn't know or doesn't care about what's inside. And also the computation is opaque. If you want to do a filtering or a mapping of that, you just pass the function to Spark. So again, Spark doesn't have any knowledge about the operation or the functions themselves. So going back to this picture, you can see that between the snapshot and the feature generator, the time machine, DeLorean itself, now we use RDD of POJOs because we build our system based on POJOs. As I said, because RDD operations are opaque, so they're at very low level, we are solely responsible for performance optimization. It's like, because Spark has only limited information about your operations or data, so it doesn't have much ability to know that how to optimize your operations. You are solely responsible for that. Sometimes that's not necessarily a bad thing, right? So if you're building a piece of infrastructure that only powers one product, you can pretty much hand tune that to the best performance. But here at Netflix, we use the same infrastructure to power completely different kinds of product. So it's very hard. It's impossible to build just one thing to fit all, like at very low level. And also, RDD operations are on the whole object. And even if only one field is required, you still need to deserialize the whole object there. For example, we have a Java object, something called like video metadata. It has almost everything, every knowledge about a given video. For example, the title of the video, the play length of the video, language, subs and dubs, everything there. But maybe in my training model, I only need the play length of the video, but I still need to deserialize the whole object, the video metadata object, and then run the dot get play length there. It's kind of inefficiency there. So, but anyway, we built that. But to address those problems, these inefficiencies, later on we rewrote our offline feature generator using data frame. So data frame, as opposed to RDD operations, data frames are pretty transparent. Transparent in the sense that first, the data are structured. It's no longer a black box to Spark. So Spark has the information. Spark has the schemata of everything. So it knows the structure, internal structure of the data. It's transparent. And also the computations becomes transparent there because you don't directly control Spark how to run, right? You describe how you want Spark to run. And Spark will analyze your plan and optimize your plan, and then compile your plan to some physical executable plan there. So you're no longer directly telling Spark how to do things. And Spark will be smart enough to optimize on top of that. So this is a very classic example, I would say, about predicate pushdown. That's how you can take advantage, one example of how you can take advantage of data frame APIs. So we have, we read the table, and then we perform some map operation, and then we filter on those rows. And the map operation can be potentially very expensive. And the filtering operation, it can be, it can filter out, say, 90% of the rows. But if we execute as is, then we have to perform mapping on all the rows and then throw away 90% of that. But with predicate pushdown, we can do the filtering first because we know that at the end of the day, only 10% of the rows will survive. We could just perform the mapping operation on the 10% of surviving rows, and we can switch around the filtering and mapping. That's predicate pushdown. So that's how we can take advantage of data frame operations instead of RDDs. So now we're going to change this communication between snapshot and DeLorean feature generation from RDD of POJOs to structured data in data frame. All right, and the generated features with label becomes structured label features. All right, here's some performance gain. We can see that using the approximately same settings, cluster settings, we observed for this particular product, we see that on average there is 3x runtime gain. So previously the runtime was around 3 hours, but with the data frame operations, the runtime was about an hour. That's pretty good. That's pretty exciting. But is that it? Should we call it a day? Well, not necessarily. If we take a look at the physical plan of the data frame taken from snapshot, so if you remember previous slide, we read the snapshot from S3 with data frame API, and then we supply those data into the feature generator, the time traveling machine. All right. So if we take a look at that part, and right after the data frame was taken from snapshot, let's run the explain there. And we can see that the physical plan here is actually, there's a step called scan existing RDD. That's odd because we're using data frame. We're no longer using RDD. And why is there RDD there? I thought we've gotten rid of RDD. Why is there RDD? So actually, what we're doing there, we added a few logic there from reading snapshot to feeding that to structured data frame to offline feature generator. Actually, we had some deduping logic there, and those deduping logic were implemented with row manipulation, right? So even if the input and output of this logic, they're both in data frame format, but how the mapping or how the conversion or transformation was done was by RDD of rows. So again, we have RDD there. With those RDDs, even if you transform the data frame, one data frame to the other using low-level RDD of row operations, even if you have the same schema from input and output, but Spark doesn't know. Spark still treats this as a black box because RDDs are black boxes, right? For example, this is an ultra-simplified example here. We have the input as column 1, column 2, column 3. And output has exactly the same schema. Okay, column 1, column 2, and column 3. But because the internal implementation of the transformation was based on RDD, right? Spark doesn't know anything. And this is how Spark sees it. The inputs are column 1, number 5, column 2, number 6, column 3, number 7. And the outputs are column 1, number 12, column 2, number 13, and column 3, number 14. They're different, even though the column names are the same. So if we want to filter the output data frame by column 1, and Spark will say, oh, you want to filter by column 1, number 12, even though I have a column 1 in the input side, but it's column 1, number 5, so they're different. I can't really push the filtering logic down to the input side. So it's stuck there. This is a big black box in between. And this is the flow. If you're going to do scan RDD, filter, and project in this particular case, and actually the scan RDD part is actually read the table from JSON, project, and explode. This is our deduping logic. But because the RDD operation, the dotted lines, it's a big black box, manipulations on the row objects are actually completely opaque. It's blocking the optimizer from moving operations around. So the filtering cannot be pushed further down there. So we don't want that. But how do we solve that? We use column operations. So most of the time, actually, the column operations we have are like columns to columns, right? We don't need to wipe out the whole row there and create a new row. We can just create a new column and replace the old one or just append that to the existing data frame, right? For example, still the very similar thing here. Say the output side, the column 3 is the newly computed column 3 to replace the old column 3 there. And it's computed based on the input side of column, say column 1, 2, 3, all of them. But actually, if you use column operations, we're telling Spark that, OK, this new column 3 is generated based on the input. But column 1 and column 2 remain the same. They remain the same. They're not changed at all. So in this case, Spark will know that column 1 and column 2 are still column 1, number 5, and column 2, number 6, right? Just the column 3 is the new thing. Now, if you want to say, OK, I want to filter on column 1, Spark will say, OK, you are filtering on column 1, number 5, and I see both column 1 or 5 on both sides of this operation, and it's not changed during this. So Spark know it can push the filtering logic further down to the input side of that. Right? This is one of the keys of column operations. And OK, there are actually 3 types of column operations. The first one is Spark SQL functions. Second, user-defined functions. And third, catalyst expressions. I'll go through them one by one. The first one is Spark SQL functions. Those are functions in org.apache.spark.sql.functions. They're built in. They come with Spark. And they're highly efficient because they're using the internal tungsten data structure. And they're using code generation. So each time you run that, the generated new code is based on your particular setting. So it's very efficient. And also, it supports rule-based optimizations. I believe there are also cost-based optimization with Spark 2.2. And there are a variety of categories. There are aggregations, collection, mass, strings, all of different types of things. So if you find one operation in Spark SQL functions can satisfy your needs, so by all means use it because they are highly efficient. But oftentimes, you don't find them in those functions. So you can do, first option you can have is user-defined functions. You can write your own functions to do your operation. So user-defined functions are Scala functions with certain types. You can't write like a UDF on any type of any types, but they're pretty good actually. There are a lot of different types you can write UDFs with, and also they are highly flexible because you are writing the function. You have the great flexibility in doing that, and also because the UDF you write is based on the Scala function or Java function, right? They're operating on the normal type of data structure. So, but actually, when Spark executes, it's in the tungsten format. So, but your data is not on the tungsten format. So there are some data encoding, decoding required here. A little bit inefficiency, but most of the time it's fine. And the third type of column operation is user-defined catalyst expressions. It's kind of like a little bit of the two worlds, the better of the two worlds. It's flexible because it's user-defined, right? Sort of like UDF, you write the function. But it's also efficient because it's operating on the internal data structure. You have to write that on the internal role instead of a normal external role. You have to deal with the tungsten format. You cannot get a column by name, but you need to know the index and get the column by index. But usually that's fine. And very interesting that you can even write your own code generation, right? So that can make your pipeline even faster. So three types of column operations: Spark SQL functions, user-defined functions, and user-defined catalyst expressions. Now we're going to change this data transformation from snapshot to feature generator. Previously, it's role manipulation in data frame format, but we're changing the role manipulation to catalyst expressions. So we're going to, we actually rewrote the deduping logic with catalyst expressions. It's something like this. So it's like, the deduping logic is a case class, which extends unary expressions. So of course, you need to write the evaluation function, and if you want, you can also rewrite the code generation function to accommodate your need. Based on this, we can see the difference here. It's no longer a black box because there's no RDD involved here. We can, the picture to the right is the real execution sequence there. We can see actually the filtering logic can be pushed down further down, right after the table scan, right? That's pretty good. And this is a physical plan. We no longer see the scan RDD. We can see that this filtering is right after the local table scan. That's pretty good. So we filter as early as possible. So with this rewrite of deduping logic and some other logics, also we remove a whole bunch of RDD operations. We can see that we have a further 2x runtime gain. So now with the same cluster setting, the same product offline feature generation takes about 30, 35 minutes. That's pretty sweet because that's money. We're running on AWS. All right. In conclusion, first we train our data based on something we call time traveling feature offline feature generation and offline training. We log facts, and then we generate features based on the facts. And also, there's some takeaways about optimization. First is we should remove the black boxes. Actually, today, Spark is very, very powerful in terms of performance optimization. Catalyst engine is something very, very powerful. But in order to take full advantage of that, you need to open up. You need to let Spark know what your data are and what your operations are, right? Because without that knowledge, Spark can't really do any optimization. And also, we should prefer high-level data frame APIs over low-level RDD APIs. And also, we prefer column operations over row manipulations because, again, it's about removing black boxes. Well, talking about high-level data frame APIs, that's very interesting is that with Spark 1.6 and older versions, data frame, if you want to map on the data frame, you use data frame.map, and actually that's RDD operation. You know, the result is RDD, but you don't necessarily know that just by looking at the API. It's data frame.map. But now with Spark 2, they changed the API to data frame.rdd.map. So that creates some itch there. The RDD is offensive, right? So you see that you no longer want to use that API. You want to rewrite that part because now you're sure that this is RDD operations and you want to get rid of them. All right, this is pretty much about that. So before we take any questions, we'd like to say that Netflix is hiring. Thank you very much.
Questions? Wow. Nobody?
Question?
Okay.
Yes. So looking at the, you mentioned user-defined functions and then user-defined catalyst expressions. I've been Googling those. I was wondering if you could point us at documentation for the user-defined catalyst expressions.
I don't think I get the question. I'm sorry.
Can you say it again? Sorry.
Yeah, I'm sorry. Oh, that's actually that's a good question. We're facing the same questions. There's some interesting, there's some documentations about that from Apache Spark, and there's some interesting blog posts about that. But I would say maybe sometimes the hard way is the best way. Sometimes you need to read the code and ask questions to Spark committers. Usually they're very helpful, but yeah.
So basically, you can check out the code. There are a couple catalyst expression, like add, subtract, this kind of stuff. And then the implementation is pretty simple. So just follow how Spark Codebase implemented, and then you can try it out in your application. And also, many of those API are private before Spark 2.2. So that's why not many people are using it in the company setting. And we work around that by putting our code on the same package as Spark. But after 2.2, many of them are like a public API, so you can check it out. Yeah.
It's good to have a committer sitting right next to you.
No, not really.
Hi.
Yeah.
Hi, I have two questions. First, is DeLorean open source? And secondly, is there any advantage to using data sets in Spark 2 instead of data frames?
Good question. For the first question, DeLorean will be like an in-house solution because it interacts with many of the Netflix microservice, and that is not generalized enough for people outside to use it. And second, by the implementation, you guys can implement it definitely. And then the second question is data set versus data frame, right? I believe. Or how is the performance penalty of data set? So it's a good question. So data set has quite a lot of performance penalty compared with data frame, but the internal data structure is the same. So if you apply data frame API, we code it on type API on data set, there's no performance penalty. But if you perform type operation on data set, there's a penalty because for even you do simple map on the data set, the whole data has to be deserialized into the class, case class. And then you do your operation, and then you convert it back to another data frame or data set. So this kind of serialization, deserialization is really expensive. And that is something people want to do. And also that will make the whole stage not transparent to Spark. So Catalyst cannot optimize it on the data set structure. But I know Databricks, they have solution on that by parsing the code inside the data set, and then you can convert it into expression. So you can talk to them. But that's what I heard. Yeah, but open source one doesn't have this. Yeah, cool.
Hi, my name is Raj. So predicate pushdown is really good. Similarly, encoders has the facility to implement the code that can really work at the file system level rather than bringing the data up, right? So if I want to do map at that file system level, I can still do map because the encoders is going to generate the code in similar ways that it can work at a file system level, right? So that piece, how how it helps in terms of encoders facilities and all, that particular way of generating the code and then pushing down to the file system and then generating the code so that we don't have to even pull the code into the JVM. Executors.
Can you say it again? I don't.
Yeah, there's a strong echo.
The question
there.
is like generating code, how it helps in terms of if it is helping, how many operations are supported right now, like.
Okay, so are you saying that how CodeGen can be helpful in terms of the in Spark SQL?
Yes.
Okay, so CodeGen can be helpful, for example, like, let's say you are manipulating a column, let's say everything is long, and then you apply add operation, add some constant, add something on top of another constant, and you can build a tree, the whole entire tree of whole your SQL operation, and then the catalyst can do optimization on top of that, and creating the whole code for the whole stage. So by doing so, even you have several operations, those operations will be encoded in one giant Java code. So in this scenario, you don't run like many operation code, because each OP code is pretty expensive in JVM. And if you can put them together in one giant function, then they will be faster, especially for some of the simple operation, math operation. Then the cost in terms of calling the function, which is a virtual code, can be quite high compared with the real world.
Yeah, and in terms of predicate pushdown, actually the predicate pushdown isn't because of the CodeGen or catalyst functions, but it's really about the operations based on the column, right? Previously on RDD level, we're just like wiping out all the columns in the same row, but now we're actually telling Spark that we're not touching those columns. We're only generating new one, even if the operation itself can be, that operation can be a black box or can be opaque to Spark, but at least it's not touching other columns.
Great. Okay. Thanks. I have one more question. Like, in terms of predicate pushdown, so it has to support even the file format level also, right? Like, data frame API. Is it not just like, if I read from text file and if I try to use filter condition, it will not even push down the predicate to the file system level, right? It has to read the data. So is there any, data frame API, is it particular to any particular format of the data, or is it generic to any format of the data?
I think that can be pushed down to the file system level.
Yeah, for some of the Parquet operation, you can push it down into Parquet.
Yeah.
Not all the operation, based on my understanding. Yeah.
Thanks.
Okay, guys, thank you very much. Please show your appreciation.
Thank you.
Okay, thanks.